In section 3.1, we discovered what extrema were and how to find those critical numbers. What we want to do now is delve a little deeper into those topics and determine intervals where our graph would be increasing or decreasing, and to use the first derivative test to help us do that. So our two objectives are to determine the intervals on which a function is increasing or decreasing, and of course to apply the first derivative test to find the relative extrema of a function and where it's increasing or decreasing. So what we've already done is learned how to find the derivative, how to set it equal to 0 to find all of the points which could be critical numbers, also how to find the derivative and determine where it's undefined, which are also critical numbers. Now what we want to do is learn how to classify the relative extrema as either relative minima or relative maxima, and we've already done that a little bit, but we're going to try to be a little bit more efficient about it. But first we need to understand increasing and decreasing. So again, this guy is the official definition, but I'm not going to talk down to you because I know that you understand what increasing and decreasing means. As I go from left to right, is my function moving upward, meaning the y values are getting greater? Well, that's increasing. Is it moving downward as I go from left to right, or the y values are decreasing, which of course is a decreasing interval? And not that you need it, but here's a nice little visual for you. So I can see that on my graph, I have, this is the point A, and this is the point B. And I'm saying from negative infinity to A, my function is decreasing because as I'm moving from left to right, it's going down. From the interval from A to B, this is a constant function. And on the interval from B to infinity, because this is going to go on forever in this direction, then that interval is increasing because as I go from left to right, my value is increasing. So how are we going to do this with the math that we've learned so far, or the calculus that we've learned so far? Well, remember that whatever f prime is the slope of our tangent line at that point. So if I end up with a negative slope or a negative derivative, then it implies, of course, that my function is decreasing. So if I have an f prime that is less than 0, then I have a decreasing function. Because if I have a function that's decreasing, say from here on, any of these tangent lines would be negative. The slope would be negative. If the derivative is greater than 0, as it is on this side, notice anytime I would draw a tangent line, I would end up with a positive slope. So anytime I get a derivative value that is greater than 0, positive slope, it's increasing. Obviously, we already know this last guy really, really well. If f prime of x is equal to 0, then f is constant, meaning that I'm going to have a horizontal tangent line. So let's take a look at how we would actually go about this using all of the definitions, because I am more of a visual example kind of person. That's always what helps me to understand, so I'm hoping that helps you to understand. Before I get started on any of the steps, I want to just encourage you to feel free to graph any of these. Now I'm not going to graph this for real because I don't want to take the time, but I know that this is a cubic function. Right? It's x cubed minus 3 halves x squared. So it's a polynomial function that is cubic, and my leading term is 1, and so it's going to look something like this, and it doesn't matter if it doesn't look exactly like this. This is what a cubic function with a positive leading coefficient looks like. Which means when I'm doing the math, which I haven't started to do yet, it would make perfect sense to me to have two critical numbers, and to have an increasing, a decreasing, and an increasing interval. So that would make sense to me. So now let's do the math. And again, you could totally do this for real on your graphing calculator or in Desmos, but it's a good idea to know where we're headed. So first, we need to verify the function is continuous. So obviously it's a polynomial function, it's continuous, check, check. Next, we're going to find the derivative of the function and the critical numbers. Critical numbers, of course, where f prime of x is equal to 0 or where it's not defined. So my original function I can derive very easily. So again, 3x squared minus 3x. Factor because I'm trying to find where it's equal to 0. F of x is equal to 0, and I find 0 and 1. Now this makes perfect sense to me, but again, not a bad idea to just double check. Is there any point at which this function is undefined? No. So we didn't have to worry about this one here. So we have two critical numbers, which is what I had originally said I would probably end up with. Now I'm going to create my intervals. So essentially, I'm looking at a number line going from negative infinity all the way to positive infinity. And I have a point here at 0, and I have a point here at 1. And so I'm breaking this into intervals based on those values. So from here to here is the interval from negative infinity to 0. This is the interval from 0 to 1. This is the interval from 1 to infinity. So these are my three intervals. And now I'm going to determine if the function is increasing or decreasing within those intervals. So before we talk about the table, I'm just going to remind us that our derivative was 3x times x minus 1. Now what I want to do is essentially I'm taking my intervals that I've just created, which are in this row obviously, and I want to find a test point. And the test point is any point that is between the two values. And it doesn't need to be directly in between. It can be any value as long as it's not one of the endpoints. So if I used 0 or 1, I'm going to be in trouble. Any other point, as long as it's between the two values, is perfectly fine. So notice I've chosen negative 1, 1/2, and 2. Now what I'm going to do is I'm going to take that number that I've made up and I'm going to plug it back in up here. I'm going to say f prime of negative 1 is 3 times negative 1, and then negative 1 minus 1. Well, that's negative 3 times negative 2, which is obviously 6. 6 is a positive number, therefore it's increasing. I've repeated that process for 1/2 and 2, and I'm not going to put you through that. But I found, again, increasing, decreasing, increasing. Now, if you'll remember back to my crazy picture at the beginning that looked like this, I said I should have had an increasing, a decreasing, and an increasing. So basically, I'm feeling pretty good about myself right now. So again, we can say our function is increasing over the intervals negative infinity to 0 and from 1 to infinity. And our function is decreasing over the interval 0, 1. These are all open intervals. Another way that we might write this one is negative infinity 0 union 1 to infinity. Another thing to point out is that those critical numbers at x equals 0 and x equals 1, notice I didn't go through the math for that, but those are of course going to be my minimum maximum values. And we'll talk a little bit more about that in a second. So to recap, what we just did is essentially we took our function, we found the derivative and set it equal to 0 and also determined where it was undefined to find those critical values. And then we used those numbers to determine the intervals. We found a test point in the interval and determined the sign of f prime of x using that test point. Then we used theorem 3.5 that said, hey, if that slope, the point in the test point gives us a positive value, it's increasing, and if the test point gives us a negative value, it's decreasing, etc. So let's look at another example. Same idea. I'd like you to try this one on your own first before I go through it with you. So if you do that, that would be great. Remember, I want you to find the derivative, set the derivative equal to 0, and determine where it's undefined. Those are your critical values. Find a test point in the intervals created by the critical values. Determine if your function is increasing or decreasing based on the sign of the derivative at that point. Let's take a look. First thing I did is said, hey, this is a polynomial. Again, it's a cubic function. It's continuous everywhere. And it's also a cubic function, again, with a positive leading coefficient. So it's going to be one of these guys again. So I should be looking for increasing, decreasing, increasing. So what I did was I found the derivative. F prime of x is 12x squared minus 6x. Then I set that equal to 0. I didn't have to determine where it was undefined because it's not undefined anywhere. I found two critical values, 0 and 1/2. I split my entire domain of real numbers from negative infinity to 0, 0 to 1/2, 1/2 to infinity. Then I found a test value in each of those intervals to determine increasing, decreasing, increasing. And then, of course, wrote my final solution. So I didn't go through a ton of the math on that one, again, because I hate making 15-minute videos. So let me know if you have questions on this, but it's the same process that we went through on the last one. Of course, my life would not be complete unless I gave you, like a hard question to do. So this one's more difficult for sure. Same idea, but we're using something we've never used before, and that is how to find the derivative of an absolute value function. So this is basically saying, do everything you just did, but oh, by the way, here's a new differentiation technique. This one says if I want to find the derivative of the absolute value of something, and in this case that something would be x plus 7, then f prime of x is going to be u, which is x plus 7, divided by the absolute value of u times u prime. Well, the derivative of x plus 7 would just be 1. Don't forget I had a 3 out front. So really, this is my derivative. So if you feel comfortable moving on, go ahead and move on from here. If you don't, I'm going to go ahead and get started now. So again, I know that it's continuous everywhere. It's not differentiable everywhere because this is an absolute value function, but that's okay. It doesn't need to be differentiable, it just needs to be continuous. So I found my derivative, which looks exactly like it looked up here. Then I just simplified it a little bit. I said, let's go ahead and pop that 3 to the top. So it's 3x plus 21, or you could leave the 3 factored. Set it equal to 0, and find any points at which it's discontinuous or equal to 0. So obviously it's discontinuous at the point negative 7, because negative 7 plus 7 is 0, and the absolute value of 0 is 0, and I can't divide by 0. If I were also to check the numerator, 3x plus 21 equals 0, I would say 3x equals negative 21, x equals negative 7, so that's really our only point. It's discontinuous there would also make the numerator 0. So just a bad idea. Negative 7. So our only intervals are negative infinity up to negative 7, and then negative 7 up to infinity. So choose some value in both of those intervals, as I have. Check the sign using the derivative, which is this guy, which I found decreasing, increasing, which would make perfect sense again, because remember, I'm dealing with an absolute value function that's going to look something like this, give or take, so it would make sense that I would have decreasing and then increasing and only one critical value. So it turns out my function is decreasing from negative 7 to infinity. I'm sorry, increasing, wow, increasing from negative 7 to infinity, and decreasing from negative infinity to negative 7.